I was interested in applied mathematics, so I did an independent study this past semester with Dr. K to explore linear programming and more specifically ways to solve linear programming problems. So I'm going to explain how the Simplex method can be used to solve linear programming problems. But first we have to go over some background information and terminology. So my motivation for exploring this topic was because optimization problems are used in everyday life, and it's a mathematical way to determine the best possible solution to a given problem. And we use this in everyday life, such as maximizing profit of a product or like minimizing fuel for a plane. And the goal is to minimize or maximize the overall value of the function. And linear programming is the branch of applied mathematics that deals with these types of problems. So the Simplex method is a way, like I said, a way to solve these linear programming problems. And again, we want to minimize or maximize an objective function, but it's subject to some number of linear constraints. So say like in real life, if somebody was looking to maximize their daily calorie intake, but they subject to like a certain amount of fat per day or and like sodium per day, then you would want to maximize the objective function, which would be the calorie function, with the constraints, which would contain like the variables for the different like the foods that we were trying to eat. So we want to find the optimal solution for an objective function, again given a set of constraints, and it's going to lie in the set of feasible solutions, and a feasible solution basically just satisfies all of the constraints for a linear programming problem. So the set of solutions is going to lie where all of the constraints intersect. So this is what a linear programming problem looks like in the most basic form. We have an objective function z that we either want to maximize or minimize with some number of variables, and then we have linear constraints, and it's important that the right side of each constraint, the b vector, is positive, and we want all of the variables to also be positive. So it's going to be useful a little later that to put, we're going to have to put the system of linear equations into a matrix notation. And the linear programming problem has to be in standard form for the Simplex method to work. So in order for it to be in standard form, and if we just go back, it's going to look like this. And okay, so if it's in standard form, it means that it's a maximization problem. All of the variables are non-negative. All of the constraints are linear inequalities, so less than or equal to, greater than or equal to, or equal. And the right-hand side b vector is non-negative. So to begin with using the Simplex method, we first have to convert the standard form linear programming problem into canonical form, which just means that we're going to set the constraints equal to the right-hand side b vector. To do this, we add a slack variable. And basically, the slack variable, we're going to add one for each constraint, and it's just the amount of unused resource from the right side that we're adding to the left side. So we do this to convert all the inequalities to equations. So this is linear programming problem in matrix notation. It's just probably looks familiar to everybody in here. And we're going to be putting this into a tableau to use the Simplex method. So I thought it was useful when I was like learning the Simplex method. I looked at the geometric interpretation first with the picture before actually like implementing the Simplex method with the tables. So here is a picture of, okay, so given a function that we want to maximize, 25x1 plus 30x2, that's our objective function, and we have it's subject to some constraints, which were changed initially into canonical form by adding two slack variables, y1 and y2. So again, a feasible solution to the linear programming problem is one that satisfies all of these constraints, including x1, x2, y1, y2, all greater than or equal to 0. So the lines that the lines that I just drew, this equation lines that are on the axis, they represent the first two constraints here, and the shaded region of the lines corresponds to the feasible solution, or the set of feasible solutions. And we are going to be looking for when, again, all of these variables are positive. So the okay, so the optimal solution, we want to start with, to find the optimal solution, we want to pick a vertex or an extreme point. So we start with 0, 0 as a basic feasible solution, and we know that, this is good, I wish I had the good point. So 0, 0 will be like right here. And we want to start, so x1 is 0 and x2 is 0. So we're looking to increase the overall value of the function. So we can either, we can do this by increasing x1 or increasing x2. And we can only increase one of those variables, and then we're going to have, we can increase one of those variables from 0 to a positive value, and then the other one we keep at 0. So for right here, this extreme point, you can see that like we could increase x1 or increase x2. And the way that we go about doing this is we look at the original objective function, 25x1 plus 30x2, and if we keep x1 at 0 and increase x2, then the objective function just becomes 30x2. And if we were to keep x2 at 0 and increase x1, then the objective function becomes 25x1. So based off just calculus, we know that if we increase x2, then the objective function has the faster rate of change. So that would increase the overall function of the most. So we want to increase x2, and we would keep x1 at 0. So the most that we can increase x2, given these constraints, is up to the next possible extreme point. Because we see if we go past this extreme point, that's when it'll become then y1 becomes negative, and it was positive up to here. So then we're violating a constraint, so we can't increase x2 any more than past that point. So then we would go on to the neighboring extreme point, and this is a little bit harder to understand because usually we'll be using more than two variables. So we would look at the next neighboring extreme point, and again, we would choose the direction of fastest increase for which variable that we would choose to leave at 0 and which one we would choose to increase. So we can see geometrically that this happens, or we can see it's easier to see geometrically, like when we violate a constraint and how much we can increase one of the variables before that happens. And also, if you're working with like more than two variables, then you have to solve for, say in this case, when moving to like the next extreme point, we would have to solve for the slack variables using the constraints and then plug them back in order to test again like which 2 points per given has the fastest rate of change, which one we would increase and which one we would leave at 0. So basically the overall idea of the simplex method is going to be looking at the neighbors of the new extreme point, and if there's a neighbor or adjacent extreme point that gives a better solution or a higher value to the objective function, then that's a new vertex, and we would pivot to that vertex and do the same procedure over again until we reach an extreme point in which none of its neighboring extreme points give a better value for the objective function, and then we know that we've reached an optimal solution. So next we're going to go into the application of the simplex method using tables, and this is just an overview of how how the table method works. First we set up the initial table, and then the initial table comes from the augmented matrix of the linear system of equations that we saw earlier in the linear program when it was in standard form. This probably won't make much sense right now, but we're going to come back to this a little later. Okay, so solving a linear problem using the Simplex method, first we want to convert the constraint inequalities to equalities by adding slack variables. So if we're given this problem, maximize 8x1 plus 9x2 plus 5x3, subject to those three constraints. Then by adding the slack variables s1, s2, and s3 to each equation, we get a canonical form, and then we would rewrite the objective function, solve for setting everything on the left-hand side, and then we place this new objective function at the bottom of the matrix. And then we're going to place the system of equations with the constraints and the slack variables into a matrix. Okay. So here you can see we have the three basic variables, x1, x2, and x3. They're called basic because they're in our basic solution. They're in the objective function that we're trying to maximize. And then the slack variables are s1, s2, and s3. And just to begin the simplex method in table form, you set the non-slack variables, so that would be x1, x2, and x3 equal to 0. And s1, s2, and s3 are basic variables. They start out as basic, so that's why they're on the left side. So now our first step is going to be, we check if the objective row with the new modified function, then -8, -9, -5, 0, 0, 0. If that row has any negative entries in it, and if it doesn't, then we know that that the solution we have is optimal and we're done. But if it does have negative entries in it, then we again recall that we reach. Then we want to increase the overall function because it's negative, so we know it has a higher value. So again, we would want to go with the extreme point method, and we would want to increase one variable from 0 to a positive value and decrease another variable that is positive to 0. So we're going to choose one of the variables up at the very top row, x1, x2, x3, s1, s2, s3, to be one of the entering variables, and it's going to enter over to this left side and become a basic variable when it increases from 0 to a positive value. And then once we increase one of these values, then one of these has to decrease, and so one of these basic variables leaves and becomes a departing variable. So then first we go about choosing the entering and departing variables. So to do that, we look at the most negative value in the objective row, and here it's -9. So we know that x2, the corresponding column that it's in, x2 is going to be the entering variable, and then we would, in order to find which variable is the leaving variable, we look at the rightmost column, next to the augmented matrix, and compute ratios for the corresponding values in the pivot column, so x2. So we would do 2 divided by 1 is 2, and then 3 divided by 3 is 1, and 8 divided by 6 is 1.13. So then the minimal ratio is, so it would be 3 divided by 3 is 1, so then that's the row that corresponds with is our leaving variable, and the intersection of those two, the pivot row and the pivot column, is the value is the pivot value. So then from here, we would want to determine the pivot element, which would be 3, and that's just where the pivot row and pivot column intersect. And so from here, we want to Okay, so once we have our entering and departing variable, then we form a new table by pivoting, a process called pivoting. So we would, it's basically like row reducing, if anyone's familiar with that. I'm sure most people are. We would want to multiply the entire row of this first pivot 3 to make it, okay, so if the pivot was k, we would multiply the entire row by 1 over k to make the pivot, the new entry in that pivot value 1. So you can see from the first table to the second table, we multiply the entire row by 1/3, and so then the pivot value now becomes 1. And then we add this new pivot row, we add multiples of this new pivot row to the other rows, including the objective function, because we want the values under this pivot value to become 0. And then we would repeat the process again of finding the entering and leaving variable by looking here. -2 is the most negative value in the objective row. And then we would again compute the ratios with the augmented values. And then the lowest, the most minimum value is the one that's the leaving variable. And so then again, we would multiply this row to try and make the 2 a 1, and then add multiples of that new row to the other rows, including the objective row. And then, so we stop once we reach, we check the objective row and see that there are no negative values in there, so then we know that we've reached an optimal solution, and here the optimal solution is 11. When the final matrix has been attained, then we can correspond the last column entries to the variables in front of the first column, and the variables that are not showing are automatically equal to 0. So then if we were to plug back in x1, x2, and x3, we would see that the maximum value of z is 11. So just to recap, the simplex method proceeds from a given extreme point to an adjacent extreme point in a way that the overall value of the objective function increases or worse will remain the same. And the method iterates until there's an optimal solution, or realize that the given problem has no finite optimal solution. And just to show you this algorithm one more time, so this is how you would go up setting up the table, and again we would first look if there are negative entries in the last row. If yes, then we would get a pivot column, and then go about finding the pivotal row, and then get a new table by pivoting. And then if no, then we know the indicated solution is optimal. And however, though, if we go to get a pivot column, and we have to see if there are any positive entries in the pivot column to use with the ratios. We can't use any negative numbers. So if there aren't any positive values to compute the ratios, then there's no optimal solution, and we would stop. So some possible ways that the simplex method could fail is if it's an unbounded problem. So then there's no finite optimal solution because all of the variables in the pivot column are negative. So like I just said, if there aren't any positive values in the pivot column, then this is because then we can't compute the ratios and determine the leaving variable, because once we start to increase the entering variable, the value of z and the basic variables would increase infinitely. They're unbounded. Also with degeneracy is when you have simplex iterations that don't change the basic solution. So if we did multiple iterations in the previous problem, but the basic solution, so like the variables on the left side, their values didn't change at all. And this is because one or more basic variables equal to 0. And typically this will end with a breakthrough represented by a non-degenerate iteration. Then there's cycling and feasible regions. Sorry. No, I want to go reverse. Sorry. But that's about it. Is there any questions?